You want to show this now? Okay.
No, I don't want to.
Oh, okay. So then let's thank Richard, and we'll continue. Okay. All right. So the next talk is actually Patrick Cousot. He has a position, and it's about the logic in program analysis and verification. And since he has worked on program analysis, both the theory and the really hard practical applications. So we'll hear. Okay, here are slides.
Yes, my context is much more restricted than the one of Leslie, and a bit more general than the one of Richard, and it's only related to program analysis. So I think for specification and verification, logic is a good choice. Leslie convinced us, but or try to. And static analysis is a different problem, and my context is only in the context of static analysis. So I am not very ambitious on this point. And so in static analysis, my slides are not well structured after the question of David Warren. In a program analysis, essentially you have to define a concrete semantic, what your language is doing. Then you have to define some abstract semantics, which is what you are going to analyze on your program. You have to have a correspondence between the two. And then you have to export your findings to the user. So that's and the user might want to specify properties. So there is an interaction with the user. And finally, you have to have an algorithm that is a representation of the analysis in some language. So for specification, many people use decidable logic because they can be checked, but they are incomplete. If you write a program with addition and you use Pressburger arithmetic, you cannot provide the multiplication. Same in first order logic, you cannot define the transitive closure. And so you go on higher and higher. And for example, in OR logic, you have relative completeness problem, and you cannot explain that in the logic. You have to explain that in set theory. And often you have properties that are hyper properties, and then it's set of sets, and it's a mess to express that in logic. So then you have to represent properties inside your analysis. That is what is inferred about the program. So I move over semantics and so on, I just concentrate. So some people use logic, and the great advantage is everything is represented in the same way. So, and for example, connective, you just put two trees together and you make one tree. And this is so simple that it seemed wonderful. But the great disadvantage is this precisely this university. It's completely, first, there is no normal form in general. And then you have completely inefficient algorithm. And for example, if you are going to represent linear equalities or inequalities in logic, it's a mess. Whereas with matrices or system of generators, you have very efficient algorithms. And so you have to move away from logic to go to these things. Another example, if you do pointer analysis, using logic to express the properties is really not efficient. You have to use graphs. So I think that logic is syntax, and syntax representation are not good encoding on information about program. Okay, so how do? We have what we call abstract domain. So it's an algebraic concept. You have a representation of properties and operation on these properties, and it's hard to translate algebra in logic. And so how do we define the semantics? By a concretization to sets. So you have both a representation and then a semantic that give you a mathematical meaning. And as Leslie said, sets are perfect. And then we also have operation, and again, sets are perfect to specify operation. Whereas in logic, it's a mess. That is, you see that I am a bit aggressive. Huh? and if you try to do proof by theorem provers, Richard had a wonderful one, but when I try, they never work. I have got a proof, then he said, poof, I cannot do it. And then you try to understand what happened, it's impossible, because even if you write 2 times the same proof, it will give you different results. That's not serious. So another thing is when you combine information, for example, you have pointer analysis and interval of values, it's not so simple. So because when you have abstract domain, you have non-uniform representation of properties. And so that becomes a problem. But we have a mechanism to combine abstract domains so that they can share information between them. And an example is a reduced product for conjunction of properties represented by abstract domain. These are a mathematical definition. You can implement them in different ways doing approximation. And it was invented at the same time as a combination of theories in SMT solvers by a Nelson open algorithm, except that they only share equalities and disqualities for completeness. But it's stupid because anyway, I am trying to solve a problem that is undecidable. So completeness means nothing. So using completeness tool is ridiculous. Moreover, you need to do induction. Static analysis is about induction. You have to go through transition and then make an inductive argument and even find it automatically. So many people say just ask to users, but if you have 1 million lines, the invariant, no one can give it to you. So in logic, induction is not part of the logic that was mentioned when you said there are a non-standard model of arithmetic in Peano axiomatization. It's because the rule of inference is not part of the axiomatization itself, and you cannot discuss it. And you cannot say, I would like to have a weak form of induction in logic because it's induction or nothing. There is nothing in between. So when we do induction, we have things like extrapolation that are based on geometric. When you have an evolution of the state space, which is represented geometrically, the induction is in the direction of growth. But if you represent an object by a formula of logic, the complexity of the object and the formula of the logic are completely unrelated. You can have a simple formula with a complex object and a huge formula with a trivial object. So it's not a basis for making induction. Okay, so that's what I was saying here. Induction is based on geometric consideration. And some people say, yes, but use abstract domains that are finite or finitary, like, for example, liquid types, but then it's completely restricted. That if you restrict everything to finite things, you cannot make Poham analysis. You can check something, but not induce properties. So my conclusion is very simple. Everything in logic is syntactic manipulation to simplify copy-paste. And that's great, and because copy-paste is simple to understand, but syntactic manipulation is not good. That's not what mathematicians do. And so logic is great for logicians to reason about proof, and mathematicians never use logic to make proofs. And here is a little theorem by a recent guy who received the Field Medal, but because of this theorem and some other one. If you look at it in French, excuse me, but if you look inside, there is logic everywhere, but there is not a single logic symbol, and all the proof is not a logic symbol at all. And if you translate that in logic, it will be thousands of pages. That's not possible. So I think computer scientists do make proof with logic instead of reasoning about proof formalized in logic. And I think that's a problem. It was a bit provocative, but it was fast, and I hope to launch a discussion.
Great, thank you.
Very nice.
Right.